blended cements. So these blended cements are PPC, OPC cement blended with fly ash slag cement, OPC cement blended with slag.
The various advantages of use of fly ash in concrete are greater long-term strength, improved workability, reduced permeability, low heat of hydration, increased sulfate resistance, increased corrosion resistance, reduced alkali aggregate reaction. Portland cement, when mixed with water, produces cementitious material. In this process, some free lime is also liberated. This free lime is the cause of porosity in the concrete. However, if fly ash is available in the mix, the free lime reacts with fly ash to produce additional cementitious material, which produces additional strength and makes the concrete denser. We spoke to Mr. Rajesh Agarwal, Deputy Chief Engineer, Delhi Metro Rail Corporation Limited, about his views on use of fly ash in concrete and RMC.
We, Delhi Metro Rail Corporation, are using fly ash mixed cement concrete in the construction of the underground structure for the obvious reasons of the strength and durability. The fly ash mixing with the cement concrete gives the obvious improvement in the workability, in the permeability, in the low alkali aggregate reaction, lesser sulfate attack, lesser chloride attack, and because of the low permeability and other reasons, there is a less carbonation and corrosion to the reinforcement, which also leads to the improved durability of the structures.
The latest statistics show that the most widespread cases of deterioration are due to the chemical effects of carbon dioxide in the air. The structure of the concrete is in very bad condition. In many points, the concrete cover has been forced out and the rebars can be seen. The calcium hydroxide present in the cement mixture creates inside the cement mass a basic environment with a pH generally above 13. The steel bar is covered with a stable and compact rust layer, which protects it from corrosion. This condition of passivity, however, is altered through the effect of carbonation. When the carbon dioxide present in the air penetrates into the concrete, it reacts with calcium hydroxide and neutralizes it, of the basicity of the environment. And with a pH below 11, the steel reinforcing bars inside the carbonated concrete are no longer protected. From the outside, water and oxygen also penetrate, thus increasing the rusting reaction of the reinforcing bars. The rust which forms occupies a volume of about 6 times more than the metal from which it originated, and so causes the cracking and expulsion of the concrete cover. As you can see, in this case, carbonation has caused considerable damage, causing the cover to come away completely. Cases of carbonation are very common and almost always associated with the use of low-quality concrete, porous and thus easily attacked by the carbon dioxide, water and the oxygen in the air. Chloride, in the form of calcium or sodium chloride, is used frequently to melt ice. These chlorides can do serious damage to reinforcing bars. Thin rust layer, which encloses and protects the steel bars, remains stable and compact as long as the amount of chloride remains below 0.2–0.3% by weight of cement. If, however, the percentage of chlorides increases, the rust layer becomes porous and no longer guarantees any protection to the steel reinforcing bars. The metal undergoes localized pitting corrosion, which dangerously reduces its diameter. Apart from the corrosive action on the steel rebars, these salts can also damage the concrete. Calcium chloride especially attacks the cement paste. What it does is react with the calcium hydroxide present in the cement matrix, forming calcium oxychloride hydrate. And this reaction produces an expansion. It causes swelling, cracking and spalling. Sodium, already present in cement or penetrating from the outside, as we can see in the cartoon, reacts in particular with certain siliceous aggregates. In this case too there is expansion and cracking, above all in unprotected structures or those exposed to moisture. This last kind of phenomenon, apart from roadworks on roads and motorways, it structures in direct contact with seawater, which also contains sodium chloride. The sea is also the place where we find, apart from sodium chloride, the most feared of aggressive agents for concrete, sulfate, which is also to be found in certain soils or natural waters. Sulfate reacts chemically with the calcium hydroxide present in the concrete mass and transforms it into the more voluminous gypsum. This product reacts in its turn with the hydrous calcium aluminates, here shown as CaH, transforming it into ettringite. This transformation also results in an increase in volume in the material with a disastrous effect on the structure. In certain very special environmental conditions, the effect of the sulfate on the concrete can be even more dramatic. At a temperature of between 0 and 5 degrees Celsius, with relative humidity of over 95%, and in the presence of carbon dioxide, the sulfate combines with calcium hydroxide and transforms it into gypsum. The gypsum, in its turn, reacts with the calcium silicate hydrates, here indicated as CSH, and the calcium carbonate CaCO3, producing thaumasite. Thaumasite breaks down concrete, changing its internal characteristics completely. Observation with a scanning electron microscope shows that the cement paste has been completely broken down. Natural thermal excursions can also cause deterioration of concrete. The most serious results are seen in freezing wet. As the liquid water contained in the concrete mass is transformed into ice, it expands and its volume increases by about 9%. The increase in volume causes internal stress. When this internal stress is repeated cyclically, the effect on the structure is disastrous.
To conclude, the various advantages of use of fly ash in concrete are greater long-term strength, improved workability, reduced permeability, low heat of hydration, increased sulfate resistance, increased corrosion resistance, reduced alkali aggregate reaction.